We're going to be continuing with Chapter 7 today, which is Big Idea 2, indicated on the board. Our focus today is going to be on determining where electrons are located in the atom, calculating energy of electrons, and also writing electron configurations. And the electron configuration will be all review, but you need to be able to write electron configurations without a periodic table, and that'll be the second half of our lesson.
Wait, without a periodic table?
Oh, did I say that out loud? Yeah, you can write it without a periodic table.
No, I know.
No, you'll get the period. I said it cockeyed. You'll get the periodic table. You won't get the subshell tree diagram. So with the periodic table, without this.
You can do it without.
I can't do it
Sure.
without that.
Yeah, but that's going to be the goal today. You can do it. There is no can't. There's no such word as can't.
Do we have to memorize that?
No,
No.
You sure?
You
I'm
just use the
positive.
periodic
you just
I never
use the
used-
periodic table.
table.
I guess if you're really good, you can do it without the periodic table.
2p6, PS2, more 2.
All right, so we're going to pick up where we left off, just to get you up to speed. What you're looking at, remember last time we talked about the inverse relationship between wavelength and frequency. As the wavelength increases, the frequency decreases. Today we're going to introduce the direct relationship between energy and frequency. Both of these equations are given to you on the periodic table, so you don't have to memorize them, and all constants are provided as well. We introduced this last time. We're going to use this. We're going to give it one little twist this year, not a big one, so it's not going to be overwhelming. A lot of theory initially with what we talk about. I have a couple of really good videos that put everything into perspective, and it's all in your notes, so you don't need to stress about it. Where we left off last time was with the electromagnetic spectrum, and we indicated that visible light is just a very small region of the entire electromagnetic spectrum. We indicated as you go from radio waves to gamma rays, the energy and frequency increase, the wavelength decreases. Multiple types of spectrum. You can have a continuous spectrum. For example, this is what you're going to see with a rainbow, where you have the whole Roy G. Biv spectrum, and a line spectrum. We're going to take a look at line emission spectra. And again, this is all written out for you. Let's take a look at what it actually looks like. So here's your continuous spectra. You have light going through a prism, and you can see that spectra. It's rained a lot this week, and I'm sure you saw the rainbows that were in the sky. I know when I took Sam to Kennedy Space Center last year, as soon as we got there, it started to rain. So we waited in the car, and when we got out, it was really cool. There was a double rainbow. Very pretty. And this is a line emission spectra. What happens here is that you have, let me pull that up and we'll take a look at the different ones. That's the same one. Let me grab it, hang on. I got it. So what you have here is you have a gas in a tube that has been evacuated of air, and you hook up an energy source to it. It's going to emit light that will pass through a narrow slit, a prism, and what you're going to see is a unique line emission spectra. Each element has a unique line emission spectra. With a spectroscope, you can get the wavelengths of those different lines, and you can calculate their energy and see what type of electronic transition occurred to get these different lines. And we'll get into that in a little more detail in just a bit. Each line emission spectra is unique. So for example, here's hydrogen. Actually, it usually has 4 lines. This is a doublet right here. Here's helium. Here's carbon. We can take a look at a whole bunch of them. That's my dancing molecule. We'll get to that in a bit. It's cool. They're dancing molecules. He does. Wait till you see them lift weights and stuff. It's really neat. We'll get into that in a little bit. But each element has a unique line emission spectra, and we'll talk about how the wavelengths and energies are related. What you're also going to see is that if you heat elements in a flame, they will emit light of a particular color, and we'll be doing this in the lab. We can take a look at this video, although I'd really like to make our own this year because I'm sure we can do a fabulous job. What we're going to look at are flame tests. And I just want to orient you for a minute. Here's your Bunsen burner. She has a pretty big flame on it. She is going to have salt solutions that contain lithium, sodium, potassium, calcium, strontium, barium, and copper, probably copper 2 ion. And she is going to put them on a wire and see what color they emit when heated in a flame. When heated, electrons get boosted to higher principal energy levels. They absorb light. And when they come back to the second energy level, they will emit light in the form of visible light that you can see. And each element has a characteristic color. You'll be exploring that more in the lab next week. We've got a 2-part lab next week, one of which is this flame testing. So we're going to take a look at these flame tests, and you'll see that each color is unique for the element, although some colors are really very close, so flame testing is not the best way to identify an element, but it still works well, and it is very fun. Now be careful, she has to clean the wire in between each one to get rid of anything that might be on the wire, and you do that with hydrochloric acid. I'm going to go through this so that we don't have to watch 5 minutes of it.
Flame test.
So the first thing she's going to do,
This is lithium. Remember that you want to be descriptive with your colors. Calling this red may not be a good description. You may want to say something about the pink.
so that looks like hot pink or fuchsia.
Because there may be another substance that we test later that also will appear.
So now what she's going to do is she's going to dip the wire in hydrochloric acid to clean it.
And heat it up so it's ready to test.
And then does she put the element on the wire?
She's doing it with a solution, so she now is going to look at it, maybe a sodium chloride solution. You don't throw sodium metal on there. So you have all salt solutions, and it doesn't matter if you use sodium chloride, sodium iodide, etc. You're after the sodium ion component. This is actually how you get the different colors in fireworks.
That sodium burns kind of a bright yellow, strong intensity.
So here's sodium, that yellowy color. Now we're going to go after potassium.
This is going to be the test for potassium.
It's like a lavender.
So potassium is a lavender.
Now years ago you used to have to memorize these. You don't have to memorize them anymore. However, there could be a color on the SAT2 chemistry. You could get a color question like this.
This is calcium. Calcium burns a bright red orange.
So that's like the orange. My fish, somebody named calcium because it's orange.
This is strontium.
Now strontium to me always made more of a red.
And calcium seem to be pretty close in color.
Here comes barium.
to go back and look at the calcium one and compare that to the strontium one. This is barium. Curious to give out the yellow-green color. Now it's gone. So as soon as you touch your substance into the flame, that's the color that you're observing.
And we'll go after copper
Put your
now.
substance into the flame. It's what you should be observing. Our last substance is copper. You can see this puts off a blue, bright blue-green color. Different than the barium. The barium was more yellow-green, whereas this is that bright blue right in the center and green.
And so you can see that each element has a characteristic color, but some of the colors are really quite close. So it's not the best identification tool, yet it does work. What I also want you to recall, we'll get into that a little, no, I'll mention it here. So what you're seeing here is, keep in mind that the oldest models of the atom in regard to electron location was, one of the older one was Bohr's model. So for example, you have protons and neutrons in the nucleus, and Bohr said that electrons orbit around the nucleus where this would be n equals 1, n equals 2, n equals 3 through 7. And what I want to remind you of is, for example, with, if this were hydrogen, you'd have one proton, you wouldn't have any neutrons, so just the one proton, and you'd have one electron in the first principal energy level. Now with a hydrogen tube, if you hook it up to a power supply, you can boost that electron to a higher principal energy level. You can swing it up to 3. And when you do that, does it absorb energy or release energy? Absorbs. So when the electron goes to higher principal energy levels, it absorbs energy. And when it comes back to the second principal energy level is where it emits energy in the form of visible light, and that's what you see. And keep that in mind. We're going to come back to this point in a little bit, but the light you see is due to the release of energy when the electron goes from a higher principal energy level to a lower, and that's what you would see with firework patterns as well. And we'll come back to that in just a few minutes. The other thing we want to talk about here are photons and energy by the quantum. And this video here does a very good job in regard to putting some of these concepts together. It's written out pretty well here, and this video, it's a little lengthy for what I typically show, but this will bring some of the concepts together.
You want to create a study website? I've already done it with Wix. Let me show you how it's done.
Now let's see how quantum mechanics helps us to understand atomic structure.
It was during the early decades of the 19th century that the structure of atoms was coming into focus. It was known, for example, that a hydrogen atom contained one proton and one electron. But the scientists of the time could think of no stable arrangement of the two particles. It was known that a proton and any atom were grouped in a small central region called the nucleus, and that the electrons were somehow arranged in comparatively large distances outside the nucleus. But in hydrogen, if the electron were stationary, it would fall into the nucleus since the charges on the particles would cause them to attract one another. Yet the electron couldn't be in orbit circling the nucleus either. Circular motion requires consistent acceleration of circling body to keep it from flying away. But the electron has charge, and charged particles radiate light when they are accelerating. So an electron in a circular orbit would radiate light and would spiral into the nucleus. Niels Bohr proposed the first working model of the hydrogen atom. In the Bohr model, the electron circles the nucleus as if it were a planet going around the sun. And with a nod to energy quantization that Max Planck dreamed up for solving the ultraviolet catastrophe, Bohr said that inside the hydrogen atom, the electron was allowed to have only discrete values of angular momentum in its orbit around the nucleus. Translated, this means the electron can occupy orbits only at certain distances from the nucleus. And Bohr simply dismissed the problem of an electron radiating away its energy by stating that it just didn't happen. Even great scientists cheat sometimes. He postulated that inside an atom, electrons only radiate energy when they jump from one allowable orbit to another.
So you're seeing that electron jumping.
Radiation reveals the allowable orbits. The wavelengths of light absorbed by hydrogen when white light is shined upon it, as well as the wavelengths of light when it is subsequently re-radiated, had been precisely studied at the time but never explained. Here's a sample of an absorption spectrum and an emission spectrum. By predicting the value of orbits that an electron could have, Bohr's model also predicted the wavelengths of the lines in the hydrogen spectrum. And his model was tremendously successful. It explained in exquisite detail the atomic spectra of hydrogen. When the energy of the wavelengths of the spectral lines are compared to the energy differences in orbits allowed in Bohr's atom, they agree exactly. So the quantum approach worked well in explaining the allowable orbit.
And what I want you to see here, for example, when the electron for hydrogen gets boosted to the third principal energy level, comes back down to the second, that's where you get this red line emission spectrum. As it goes higher and higher to the sixth principal energy level down to the second, that's where you get this blue-violet. So you can see with the smaller jumps backward, if you will, you get energy in the form of light of greater wavelengths, smaller energy.
Orbits. But no one was certain why only those orbits were allowed. In his doctoral dissertation in 1924, Louis de Broglie put forward a simple idea that significantly advanced the understanding of the extremely tiny. A quantum leap forward, you might say. Since Einstein and Planck and Compton had firmly established that light could have the characteristics of both a wave and a particle, de Broglie suggested that matter particles, protons, electrons, atoms, billiard balls, could sometimes act like waves. And when this idea was applied to Bohr's atom, it answered many questions. First, the allowed orbits had to be exact multiples of the wavelengths calculated for the electrons. Other orbits produce destructive interference of the waves, and soon the electrons couldn't exist there. So the circumference of the orbit must equal the wavelength, or twice the wavelength, or 3 times the wavelength, or for that matter, any multiple of the wavelength. Second, these orbits weren't really orbits in the traditional sense. These electrons didn't travel around the nucleus in a circle. Rather, they took the form of the standing wave that surrounded the nucleus entirely. The exact position and momentum of the electron particle could not be specified at any given instant.
And that's known as Heisenberg's uncertainty principle.
De Broglie's particle waves seem to answer many questions, but this was still not the final answer. What the heck?
He's so cute. But the video actually does put a lot of what we're going to mention and have talked about into perspective. First thing we're going to take a look at is Planck's quantum hypothesis. It says black body radiation is the release of some of the energy of a system of vibrating atoms as electromagnetic waves. And what Max Planck was able to establish is there is a direct relationship between energy and the frequency of emitted radiation, and it works for all frequencies. We can see either the absorption or emission of electromagnetic energy, and it's always in discrete amounts. The smallest amount of energy is called a quantum, and that's going to lead him to his quantum hypothesis. Energy can be absorbed or emitted only as a quantum or as an exact multiple thereof. So energy is equal to Planck's constant, which is given to you on the formula sheet, as well as the formula times the frequency. The first problem is a straight honors level question. Don't foresee any difficulty there. Planck's constant, the frequency is given here. Plug it in and solve. The AP example I want to mention, because this would be without a calculator, which you do need to get into the habit of doing. When you do your practice quizzes, all multiple choice questions will be non-calculator based. In the AP example shown here, it's asking for the energy. We know energy is equal to Planck's constant times the frequency. We have 6.6262. This is written in your notes. I want to show you the tricks. Joules seconds, and it's 6.00 times 10 to the 14 seconds to the negative 1.
This is 6.15.
This is the second AP example. So you can see the cancellation of seconds with seconds to the negative 1. That'd be S over S is 1. Now without a calculator, what is 6 times 6?
36.
36. What's 7 times 6?
42.
42. So we're about 40, right? Give or take, doesn't matter. Maintaining my sig figs. 10 to the negative 34 times 10 to the 14 is? Negative 20 is correct. You add the exponents when you multiply. And now this is 4.00 times 10 to the first. 4 times 10 is 40 times 10 to the negative 20. And now you can see 4.00 times 10 to the negative 19. And you don't have to show all those steps in multiple choice. Most of you can just do it in your head and let it rip. Until you get comfortable with it, you may want to do the steps out. Non-calculator based question. Not difficult. Got to know your math tricks, which you definitely learned back in middle school. The only thing we're going to do with this formula is figure out joules for photons per mole. That's the only difference we're going to make in just a minute. What we want to do is we want to link light and electrons, and we can do so through Einstein's photoelectric effect. He's going to use the quantum theory to explain the photoelectric effect. What you're going to do is all written out here. I'm going to show you the PhET simulation. What you have here, we'll start with sodium, pretty active metal. We're going to hit it with light. If we initially have it at very low intensity, even in the violet region, when the light hits the surface of the metal, an electron represented by these little balls is emitted. As you up the intensity in that violet region, you can see more and more electrons are emitted when the light strikes the metal. If you change the wavelength, so your wavelength increased, meaning your energy and frequency decreased, you can see that the electron emission has ceased. We can up the intensity, but it doesn't matter. As you go lower and lower in energy and frequency, you're not getting the electron emission. As you increase the frequency, you're going to get it. It is metal dependent. So whereas this one, you can see the electrons being emitted, you don't see that to be the case in this region with zinc. Although if you go, for example, here again, no. If you go in the UV region, you will. So it is metal specific. It depends on the intensity and the frequency of the light source. Photoelectric effect links light to electron ejection. You can calculate the energy of a photon using the same formula that we used previously. So if you wanted to calculate the energy in joules per photon, it's going to be the same type of formula, but we want to link these two formulas together that we talked about earlier. These were the initial formulas. We introduced this last time, this one this time. I want to derive a formula that shows the inverse relationship between energy and wavelength. So I've got frequency in here. If I solve this one for frequency, I have frequency is equal to the speed of light over the wavelength. And then I can do substitution like you did in pre-algebra, subbing it right in there. I'm going to get energy is equal to Planck's constant times the speed of light over the wavelength. Easy formula to derive, not given, easy to remember. Both constants are on top in the numerator. So this is a formula that shows you the inverse relationship between energy and wavelength, the same way you saw it with hydrogen's line emission spectra. The greater the energy, the smaller the wavelength. Also, what I want to remind you of, especially since so many of you were out the other day, we know that 1 meter is 10 to the 3rd millimeters, or 10 to the 6 micrometers, or 10 to the 9th nanometers. Visible light is in the nanometer range, and as a result, we talked about the other day how you must have wavelength in meters or you won't get cancellation of units. So if you're given nanometers, you need to convert to meters before you do the calculation. In the problem on the screen, it says calculate the energy in joules per photon of UV radiation that has a wavelength of 235 nanometers. Okay, 235 nanometers. So, if you don't see how to get meters, we mentioned this the other day, 235 nanometers, when you want to convert to meters, 1 meter is 10 to the 9th nanometers. Even without a calculator, that'd be 235 times 10 to the negative 9th meters. Nanometer cancels, is 2.35 times 10 to the negative 7 meters. Easy conversion can be done without a calculator. You've just got to watch your math. Careful. Once you get that conversion, it just becomes a plug and chug situation. You've got your constants on top, your wavelength in meters, and an energy of about 8 and change times 10 to the negative 19. And visible light typically is 10 to the negative 19th joules. What's new is this next piece. Often it asks for joules per mole of photons. And this is where you have to multiply by Avogadro's constant. You will recall on the very first quiz, I asked you to tell me how many atoms were equivalent to a certain mass. They provide you with Avogadro's number here, abbreviated Na, 6.022 times 10 to the 23rd moles to the negative 1. Doesn't matter if you have atoms per mole, particles per mole, molecules per mole, photons per mole. Here's what you're using. You can put anything in the numerator of that particular unit. So when they ask for the joules per mole of photons, you've got one additional piece here. You've got to put Avogadro's constant in, which is right here. And so you do the problem the exact same way. You have the same thing here. Basically, you're just multiplying this by Avogadro's constant, and you're getting energy 2.99 times 10 to the 5th joules per mole. Okay? The other thing I do want to mention, since we're on conversions, is sometimes they will do megajoules. And 1 megajoule is 10 to the 6 joules. 1 megajoule is 10 to the 6 joules. So that's another conversion you're going to want to know. $1 million, if you have $1 million, 1 times 10 to the $6. We will link this concept with another concept in about 10-15 minutes.
So would a megabyte be 10 to the 6th bytes?
And a giga, and a tera.
Well,
I wonder where they got tera from though, like a terabyte. To me, I'm thinking tera, like a holy tera.
pretty sure that's a prefix.
Yeah, I guess it is. I'm just not familiar with it. It's not something I grew up with. We had bytes way back when. All right, so at this point, Planck and Einstein, they said energy is quantized. It occurs in discrete units called quanta. And you'll see that electromagnetic radiation, as that strange gentleman at the end indicated, a dual nature of light, because you'll see that electromagnetic radiation shows properties of both waves and particulate matter. In regard to Bohr's model, you've seen a little bit of this already. There's one point I definitely want to hammer. It'll be an introduction to Coulomb's law. It becomes critically important this semester. Bohr was able to combine ideas from classical physics as well as quantum theory to explain the structure of an H atom in regard to the location of the one electron that hydrogen has. He felt that the electron and the proton were held together by some force of attraction, and this became known as Coulomb's law, or Coulombic attraction. It says force is directly proportional to the charges of the species, the electron and proton respectively, and inversely proportional to the square of the distance between the two particles, that is the positive proton in the nucleus and the location. You'll see that as charge increases, force increases. Not going to see much of that here, but you will later on. but this is the portion here that you want to be comfortable with. As the distance between the electron and the nucleus increases, what happens to their coulombic attraction? Decreases, inversely related. So the farther the electron is from the nucleus, the less force between the nucleus and the electron. Now Bohr talked about electrons in orbits. He said the energy of an electron is proportional to its distance from the nucleus. You can calculate the energy of an electron. We're not going to do it. He said that electron energy is quantized. You could calculate those values. When the electron is far from the nucleus, very far, the energy is 0. The lowest energy level has an N of 1. The highest energy level is going to have an N of 7. As you move away from the nucleus, in terms of that electron moving away, it's going to absorb energy. When it comes back toward the nucleus, it releases energy. When it comes back to the second principal energy level is when you see energy in the form of visible light. You can calculate the energy of an electron. We're not going to do this anymore. We're not going to worry about that. But what you do want to be comfortable with is shown here. I'm going to show you a bigger image of this because it's a little bit small. It's going to be the same image. What you're looking at here first, again, the electron from the first principal energy level can be boosted to the third. It comes back to the second or to the fourth, etc. These are going to result in those different colors of light. So, for example, when the electron goes from the third to the second is when you get red light. The fourth to the second is when you get green, etc. So this shows the electronic transitions in the Bohr model for a hydrogen atom, and you can see the correlation with line emission spectra. The last couple things I want to mention before we break. This is a very new piece. It's something you have to feel comfortable with, and we'll try and get you there. Okay, we're going to take a look at the different radiation types from low energy microwaves to higher energy X-rays. The X-ray component, as well as the visible and UV, won't be made more apparent until we talk about ionization energy and PES diagrams. You can see as you go from microwave to X-rays, the frequency is doing what? Up or down? Up. The energy is up. So the wavelength would go down. What you can probe with microwaves is the spinning of molecules, molecular rotations. Lowest energy, you can rotate the molecule, and that's literally just spinning it. Let's take a look. This is adorable. You're going to love it. So this is, let's take something simple first. Here is ammonia, and all we're going to do is spin the molecule. It's just going to rotate. Now what we're going to do is we're going to supply a little more energy, and we're going to cause molecular vibrations. So in the infrared, if that type of energy is provided, now you're going to, so that's going to be a molecular vibration. All right, these are little dancing molecules. We'll take a look at a few different ones. If you want to eject a valence electron, cause it to transition, you need to be in the visible or UV light region. And if you want to remove a core electron, that's a non-valence electron, you will use X-rays of higher frequency and higher energy. but you've got molecular rotations with microwaves. That's very easy to remember. When you put your food in the microwave, what does it do? It spins. Rotation goes with microwaves. They often ask this. Vibrations, infrared. Just remember, like an IV, what they'll hook you up to if you're dehydrated or need antibiotics, etc. And then if you look at these little molecules, now ammonia's pretty easy. Let's take a look at a bicarbonate ion. You can see the rotation. Here comes the vibration. And you can do them differently. Like you can like look at different ones, wiggle, wiggle.
Oh my.
It's so cute.
Why does it vibrate differently?
It depends on where you hit it. So here's the spin.
Like the bond angle?
Well, let's take a look. Hang on, let me let it spin.
Thing with the balls and the screws.
Yeah.
Yay.
Here, let's look at the vibration. Here's N1. Let's see. I don't think you're going to follow, but we're taking a look here. Here comes N2. So you're getting more here. N3, I'm guessing you're going to try and do this one. Wiggle, wiggle, wiggle. They're so cute.
It looks like
Here's an easy one, though. They don't actually list them in order of simplicity, which is a shame.
What?
Oh wow.
That's kind of funny.
Yeah, I love how they show.
But most importantly, what type of electromagnetic radiation causes molecular vibration? Infrared. That's what you have to be able to do. So it's fun to look at, but you really want to be comfortable with this aspect.
That looks like an omelet.
The other piece of the puzzle that I want to mention in regard to this table, and this is where really putting concepts together is critical. Previously, we calculated the energy per mole of photons, and we had about 3 times 10 to the 5th joules. Joules. So if we had 3 times 10 to the 5th joules per mole, and we wanted to get to megajoules, we're going to have 1 megajoule and 10 to the 6 joules, and that's going to be 3 times 10 to the negative 1, or 0.3 megajoules, right? So if you can calculate that, now as you look at a chart, in what region would that be?
Visible.
Somewhere in here. And so you could pinpoint the region of the electromagnetic spectrum. So if they asked you to calculate something and then identify it, they'll give you this table. They may not tell you the aspect pro, but they'll give you the first 3 columns of the table. You've got to be able to synthesize concepts, so that'll be important.
You forgot indigo.
Indigo.
Why did you go?
I did.
Where'd you go?
I wonder where it went. All right, it's back. Indigo's a pretty color. Somewhere between blue and violet. All righty. So last couple things I want to mention before we take a break, and in the second half we're going to talk about electron config. Any questions at this point? There's a lot of review, a little bit of new. So you know the new stuff's going to be assessed. Ground state versus excited state. When electrons are placed in their lowest possible energy levels, we say that we've got a ground state electron config. When not, you've got an excited state. This is what happens when the atom is provided with an alternative or an extra energy source and the electrons go to higher principal energy levels. Those of you interested in fireworks, there's an excellent article in your textbook that I would recommend. The video mentioned Broglie's equation. You don't need to be familiar with this anymore. What it does say is that a particle with a mass moving at a certain speed will have a wave nature consistent with a certain wavelength. You don't have to be able to calculate that anymore. It also mentioned Schrodinger as well as Heisenberg's uncertainty principle. Schrodinger developed a wave function. It talks about the energy state of an atom, but more importantly, it talks about the 90% probability of finding an electron in a particular region in space, later known as an orbital. And Heisenberg's uncertainty principle mentioned that with electron movement being so fast, it is impossible to determine its exact location at any particular moment in time. And as a result, Bohr's model fails. And electrons are not in orbits, but you're going to see they're in orbitals. And we'll talk about this in the next piece that we'll do after the break. But I also want to mention that you are not responsible for quantum numbers anymore. So I'm going to really truncate this and focus on showing you how to write electron configs with a periodic table only, no subshell tree diagram. And you want mastery of that concept before next time. So I'll hold off there. At this point, you want to be comfortable a little bit with the theory, being able to navigate this table, knowing if they mention molecular rotation, you could tell me microwave. This video is here for those of you who want to watch those dancing molecules some more. Bohr's model, as well as being able to calculate energy from wavelength for a photon and per mole of photon. Make sure you look at the wording there. The lab we do will get into that, but that could be very important. I've seen those types of questions on short part 2 questions recently. So you want to be comfortable with that. And we'll pick up with electron config in the second half.